The purpose of this video is to really dig into some more of the technical depth of the furnaces for two purposes. One is just to give some background information for anybody who is interested in how they operate. And number two is to touch on some of the areas that we're going to explore in the next session when we talk about what doesn't work quite right. And in order to go through that, we need to kind of understand how the various components fit together, what they are, how they work, and so on in theory, since most people probably are not terribly familiar with some of these concepts. The furnaces that we chose to put in are Stirling furnaces, and I'm just going to show you some paper drawings of these things, and we'll have some video later on of actual footage of the units. But this is what they look like. They're big steel boxes, and I guess the first thing that people notice is that there's a lot of furnaces. There's 5 of them down there, and they're big, and there's a lot of ducting. So the deal there is that if you look at these, they're modular. The bottom section is where the blower is. This section here is where the flame is and the controls. And this section is where the air conditioner coils will go. And then off to the side is the mixing box. It's actually bigger than even what this picture shows. The reason they're fairly large is because, if you notice, these are all modular. These are all bolted together. We had to get them in the door. Most commercial furnaces would be smaller than this, but still bigger than one of these modules, and would require knocking out a basement wall. And that's a major project here because it's reinforced concrete, poured concrete. We don't have like just a doorway we could open or something. So they had to actually take the block windows out to bring them in. But this allowed us to get the furnaces in. So these are SVF, Stirling residential, commercial, indoor vertical furnaces, and they come in this modular arrangement, and they have a whole variety of options that also come with it in terms of controls, and that's what we're going to go through here in somewhat great detail. Okay. Let's take a look at, they're all essentially the same. Each one's a little bit different air volume, a little different BTUs depending on the area that it's serving, but functionally they're the same. Okay, I think this is about as good as we're going to find for a picture. We're not going to go through this front too much, but if you look at the top part, this is the forced draft that brings in combustion air. You can't quite see that part here, and this is what blows it back out again, the exhaust out to the side of the building. This is the actual burners, and the heat exchanger up here. This unit down here is behind there is the blower, and this is the controls section where we have the ignition, the flame control, and various relays for dampers and things of that nature. So the way these manufacturers of the furnaces handle this is they come up with this hairy Hazunga part number, and it's in this case 16 positions, and each one of those positions specifies a different one of the options that's available, and when you put it all together you end up with a unique part number, and then they build it especially for us. So we're going to talk about the features that are either interesting, to me at least, and or are relevant to the next video when we talk about where we're having difficulties between what is supposed to happen and what has actually happened in terms of functionality. So the first one is gas control, the GC option. The gas control, and what we have is the K option, which just simply means that we have electronic modulation with duct sensing and an override stat. Okay, and we're going to go through that in depth, but we've talked about that in the past video where the flame actually modulates, whereas over here you have 1 stage or 2 stage. We have infinite stages essentially, where the flame can go up and down as needed, and then it's also predicated on the duct sensing the discharge air in terms of how or what level that flame modulates at. The supply voltage, the only reason that's interesting is because it was wrong for like 2 years. So we're going to talk about that, the supply voltage, the voltage type, and then the air control and damper arrangement is of interest to us, the AC option. And we have the N option, which means we have outside and return air interlock dampers, which we've talked about, that mixing box, with modulating spring return damper motor and an enthalpy controlled economizer, which we have not talked about yet. So if you look in here, you can see that this is where the controls are. And for the most part, it's like any other home or small commercial gas forced air furnace. It's got an igniter ignition system. It has, a transformer to step down the voltage to power that. In this case, it's got a forced draft so that the air for combustion is brought in from the outside. It goes through, supports combustion, and then it gets blown out through the blower outside, all in a sealed system. That's fairly common, I guess, in even residential furnaces these days. The heat exchanger, all that kind of stuff. So let's talk about that gas control. It's put out by Selectra Maxitrol, and there's a variety of different models available, and the one that came with our package deal with the Stirling furnace is the Maxitrol Model 21. So the Model 21, this is it here, and it consists of a variety of components. There's an amplifier, an A1010 amplifier, and that is what sits right inside the control panel of the control area of the furnace, and that takes the discharge air temperature, amplifies it, and actually drives then the gas valve open and shut in a modulating fashion, so it has to amplify that signal so it can do that. There's an override stat, which we'll talk about. This here is the sensor that goes in the discharge air ductwork. It's just a tube with little holes in it, and then it picks up the temperature from that. On the outside of the unit is this temperature selector, which is ranging from 50 to, I believe, 90, 95, something like that. And that is what sets the desired temperature for the discharge air. Here's the modulating valve. So we get all that stuff with our package deal. Okay, so let's just draw up. The Model 21 is a unit that is specifically designed for regulating temperature based on discharge air. So it's typically used for a makeup air system. And if you recall, the makeup air system doesn't intend to heat the space. It just refreshes the air, replenishes the air with outside air and recirculated air through filters, and then it adds a small amount of heat content so that the temperature doesn't drop because of the outside air being mixed in with the return air, and it runs continuously. And quite often there's two systems in a commercial building. There'll be a makeup air system and a heat system. In this case, the furnaces have to serve both roles of makeup air and heating mode. The Maxitrol they chose is the Model 21, which is the one that senses the discharge air temperature and then modulates based on that. So it's pretty simple. If you just look, I'm going to go into this detail and you'll see why in the next video, because this is a pretty big area that doesn't work, and there's just no reason why it shouldn't. So here's the Maxitrol amplifier, the A1010, and what you have hanging off here is that valve. So it's just going to supply a signal out here that ranges between 0 and a couple of volts to force that valve to go open or shut in a modulating fashion. And it's going to do that based on the temperature of the discharge air. So we're going to run a signal out here, and this discharge air sensor, this guy right here, is going to be out here. You see that? And it's going to be in line with a set point control, which is that guy right there. And it's going to come back like this. Not very nice drawings. So we're going to set, let's say, 65 degrees on this thing, or 55 degrees, whatever we'd want. And the discharge air is going to say, oh, it's only 60, so I'm going to generate a signal that says, proportionally, I need to open this valve, maybe 20% or so. If this drops way down, then it's going to open this more, and vice versa. So it just amplifies that signal. If there's a small difference, small valve opening. Big difference, big valve opening. That's all that does. Okay, of course, there's power coming to this thing, and there are some options here. So our package, this package K, came with an override stat, which is a fairly good idea, but in practice it's not all that slick. But it's a way to combine the makeup air functionality with the heating functionality all in one unit. Because right now we have makeup air where the gas valve is going to be regulated to keep a constant 65-degree discharge air. So that's fine as long as we don't have a call for heat. But if we have a call for heat, right now, there's really no place for it to occur. So what they have is this discharge air, and it looks like this. So first of all, it's this mechanical clunky knob, and then it has a switch, which is not pictured here, that activates it. So you would have hanging out on the wall that knob, like that, and then you're going to have that come over to a switch, which is probably going to be in the boiler room, and it's going to come around like this and like this into the unit. So for example, if we wanted to have this thing set at 75 degrees, it also has a temperature sensor in here. So it's going to measure the ambient temperature, and if the switch is turned on and the discharge air is 65, the room is probably going to be somewhere, around 63, 64 degrees. And if this is turned on to 75, then this thing is going to be sensing that 63, 64 and turn the circuit on, which will then open the valve up more than it was before, because now it has to do a temperature rise of an additional 10 degrees. So maybe it opens at 30 to 40%, something like that. I have no idea. And then as it gets closer, this would then modulate down. So as it just becomes closer and closer, just to the point where it meets that temperature, this goes off, and then the discharge air once again takes over and modulates to keep that at a temperate level. So, which is fine. I mean, it's a nice solution. The problem is you have to use this thermostat because of that proportional differential. It has special wiring for that, and it's a big mechanical clunky knob and a switch. So we would literally have to flip a switch to do temperature control and then have these knobs, and the setback would have to be done through some other means, which gets to be even more complicated and kind of clunky. So, in theory it's nice because it lets us have both modes, but in practice it's just not a very elegant solution. We do have 5 override stats, and they were towards the second year of construction going to put those in because we were having a real problem with this, and we'll get into that in the next video, but fortunately they didn't. Otherwise we would have 10 thermostats hanging on the wall. The other major control is the air control and damper arrangement, and we have option N. There's a whole bunch of options here, but this is those dampers and the motor and the modulation between the return air and the outside air that we talked about in a previous video. This is done by a W859F economizer control from Honeywell, and there's a bunch of components just like the Maxi-Trol, but what it includes is this is the motor that actually sits in the mixing box that has then linkages coming off of it to move the dampers back and forth. This silver part down here is the motor, and then the black cap on top is the controller, the actual economizer itself, and then if you can see there's 2 knobs up here for adjustment. You have to take the caps off of them to get inside because they're typically set once and then locked down. Now you're going to notice that if you look through the literature here of this or the Maxi-Trol, there's not just one drawing, there's not just one configuration, because these are controls that are made for a wide variety of applications. So this is part of the disconnect we're going to find in the next video, that they give you example after example of how they could be hooked up. And Sterling, in their diagrams, or in their furnace, documents their stuff in terms of like the ignition and the wiring for the motor and all that kind of stuff. But it's really up to us, to a controls person, to finalize how these are specifically wired to meet our needs. So that's going to be the gap. But there are some really good drawings and really good diagrams and examples in here but unfortunately not one of them is dead on to what we want. A lot of them are very close, and it requires an engineer really to sort that out. So what you get with the Honeywell economizer is several things. You get the motor. So the economizer, and the reason they call it an economizer is because it's really mostly about air conditioning or cooling, and it's used to bring in what we call free cooling in the summertime or in the springtime instead of air conditioning. If the heat content of the air, like overnight, is less than what is indoors, we can just, instead of having the air conditioner run, the compressor run, you can bring in outside air for a period of time and then at some point phase in the air conditioning. So you get to save a great deal of energy by using that free cooling. So that's really what it's about, but it's also used to mix the outside air for regular heating season and cooling season makeup air. So the economizer includes the motor that turns the dampers with those linkages, and a controller, of course, itself. And on the controller is one of those knobs on there is a potentiometer, which is the minimum outside air percent. So when it goes into occupied mode, in other words, when the fan line of the thermostat turns on, then it's going to shift the dampers from the normal position of being 0% outside air, 100% return air. It's going to shift them over to whatever percentage that is. So if we say 10%, then it's going to move them over to 10%, and it can't go below that as long as that fan line or that occupied line from the thermostat is activated. So that's right on the box there, and there's actually an option, which would be a really nice option, but we do not have that, is to bring that outside, because this economizer is inside the mixed air cabinet, so it's not really in a very friendly position. But over here you can see you have this remoted potentiometer, which would just be a knob in a box outside the furnace that would allow you to change that somewhat. And we may want to have a range that doesn't go all the way to 0, but would let you have some flexibility, because these numbers, the 10%, 12%, 20%, and so on that you're going to see, are all based on maximum or theoretical occupancy for that space. But if we only have a third or a fourth of the place occupied and it's really cold out, there's really no reason to bring in that much outside air, and we could turn it down. Or conversely, if it's people are active and we're doing like some kind of church or what have you, or painting, things like that, we may want to crank it way up and just get some serious air flushing through the building. And that's would be a nice feature to have, and it's pretty basic. It's just a potentiometer and a piece of wire, so that would be something to add someday, I would think, just for convenience and for energy savings as well. There is another temperature sensor, and this one is a doozy. It's this coil that's 12 feet long and filled. It's a capillary coil, and it's filled full of fluid, and it goes back and forth and back and forth and back and forth in the mixed air chamber. And the reason it's so large is because it needs to average the air temperature in there so that it gets the uniform reading across the entire surface area that is becoming the mixed air supply to the bottom of the furnace, where it gets sucked in by the blower. And that is the mixed air temp, and that's not used at all for heating or makeup air in heating mode or heating season. It's only used in the summertime, and that keeps it from having the air go too cold. So if if the air conditioner is running, or if it's really cold outside, then that allows it to counterbalance, because if you want it to cool off, you certainly want to have the air as cool as possible, but within reason. You don't want it to get too cool, and this will then say, okay, if it's like really, really cold outside, we're not going to just like open up the outside vent 100%. We're going to back it off a little bit so that we don't go below a particular sense. And that might be like 52 degrees or so, somewhat, a couple of degrees less than what the discharge air temperature is on the makeup air unit, the Maxitrol. I think that's usually a 2 or 3 degree difference, but again, that's something that really is for the professional balancing people to tell us. There's also a changeover in here, which switches it from heating season and cooling season, so that if you're in heating season, it's all about bringing in fresh air or the outside air gets closed. So it's really between 0% and this minimum, 0 and 10% or 12%, but you wouldn't ever go above that in terms of fresh air. In the summer mode, it would be all the way open. You could go from 0 if we're not occupied to 10% if we are occupied to 100% outside air if we need to have that much cooling, and that much cooling out is available. It also has a compressor lockout, which is just a line that goes to the compressor. If we do get air conditioning, that says that if we are in cooling one mode and we're trying to get free cooling, don't let the compressor get too smart and try to turn on. So we just basically have this line going to it that disables it and says you can't run until that line tells you that you can. So it doesn't defeat the purpose of the free cooling. And the last component that's included is something called an enthalpy control. And we'll talk about that in another video. It's a sensor that is in the outside air duct that senses temperature and humidity, which combined is enthalpy. In other words, how much energy is in that air. And between the two of them, and by setting a knob on the outside for which part of the country we're in terms of climate, it will be able to determine if it can use free cooling and how much. Because, as you know, it may be very cool outside temperature-wise, but with a lot of humidity, there's not much comfort in that. Or vice versa, it could be actually fairly warm, but if it's dry, it'll be able to get free cooling out of it. So it's fairly smart. It can combine those two, and then if it has to give up completely, it just shuts off that outside air and turns on the compressor. But more realistically, it's going to be somewhere in between, where it mixes some of that outside air that has a low enough heat content and the compressed air together, and modulates it back and forth to get the maximum economy out of the system. Now for us, we don't have the air conditioning yet, although these units do have the controls and they're ready to go. That's why this stuff is in there. We have the full economizer and the controls and everything. All we need to do is put the coils in and the compressors up on the roof. So we're all set to go. All we need to do is put the coils in and the compressor up on the roof, and of course the piping and wiring, but we're ready to go. But even so, we can still use the economizer to an extent by saying that we can have free cooling. So instead of just saying, just open up the outside air damper and let it run all night, it'd be better to put it on cool. One, let the enthalpy sensor be set to the correct season or the correct part of the country for free cooling benefit. And then as the night progresses, if it gets cooler or less humid, it's going to take more advantage of that outside air. But if for some reason a front comes through or something, it's all heat and all hot and humid and something, the space could have been cooled down very nicely, and then all of a sudden it's going to get all hot and sticky at the last couple of hours. In this case, it would shut it down for us and just recirculate air at that point. And then ideally, we would hook in our window air conditioners to one of the thermostats, so that would be the stage 2 cooling. And once the stage 2 cooling is on, then the outside air free, we would have that shut off unless. Real quickly talk about a few last details of the furnaces. There are 6 ducting systems that are down there for 5 furnaces, and that's why there's so many ducts and tubes and things going on. First of all, as I mentioned earlier, it has combustion air that is sealed. So we have one of the white tubes coming in, and that brings in combustion air, which is the air that is required to make the flame. Instead of sucking it out of the room, it actually brings it in through one of those tubes from outside, does the combustion, and then forces it back out from a blower. So it's a forced draft. So there's two ducts there, the fresh air, or the combustion air coming in, and the flue going out. Then, as you noticed in the previous video, we have return air coming in from the wall registers and supply air coming out of the furnaces. And then lastly, we have outside air coming in from the roof, and we have relief air going out the roof based on just the pressure of the building pushing it out. So there's not actually a duct for that you can see, although there is up in the attic and behind the scenes where you can't readily see it. So let's quick run through the furnaces that we have. There's two furnaces that we call S1A and S1B, which are the dual furnaces. And they're two identical furnaces, but they're hooked together. So if we look at them cross-sectionally here, great diagram, they share a return air plenum, and their supply air, the discharge air up here, is combined. This one goes over and joins in with this one, and then they both go up. So these are combined. They always come on together. They always shut off together. They're just basically dual together. And again, the reason why we had to do that is twofold. One is that we needed to have the capacity, not so much for heating, because we could get enough BTUs in one of them to heat the space, but not if we have to have the required air exchange. We're talking a great deal of air exchange in the sanctuary for a capacity crowd. So essentially one of these is doing nothing but just doing makeup air. So in normal heating mode, we wouldn't even need both of them, but they are dual together, and they both need to run together. Otherwise, there's no damper or anything in here, so if only one was running and there was the blower here, the air would just kind of go around and around and around. It wouldn't really go up and over because that's a whole lot more pressure, back pressure there to go against. So they do have to run together, but the other reason why we have two is because we couldn't get one bigger one in here because of the fact that there is no way to get it into the building. So again, we had to go with these vertical furnaces that are modular, and to get enough capacity for the sanctuary, that's what we need to do, is dual these together. So they have each one has their own Maxitrol, each one has their own economizer. They're complete units. The only thing that's combined is that they have one thermostat, and they are parallel together so that when the thermostat calls for heat, they both go into heat mode. When it calls for makeup air, they both go into makeup air, and so on and so forth. The supply air for this guy goes all the way up to the attic, so it goes up 3 stories, and it's a very large duct. It goes all the way up a vertical shaft up to the attic, and then it goes over and drops down into those 4 very large vents up on the ceiling, if you notice in the sanctuary. And then lastly, there's vents on the back wall of the balcony that are also connected to those vents. So it goes up, it splits, goes to 2 vents in the sanctuary, and then the 1 vent in the balcony. The return air is kind of interesting. If you've noticed the mushrooms on the floor, those are the return air inlets. And it's a really good system. It's very old, and some people think it's like antiquated and so on, but it's a really intelligent system because there are 100 and some mushrooms on the floor, which means you're going to have very, very even heat. Instead of having a modern building, if you think about some of the buildings you've been in, they have these really high velocity ducts of air rushing in, and then just 1 or 2 return vents, and you can actually feel the air moving and feel the temperature difference if you're closer or far away, not to mention all the noise. This system is very, very quiet and has those gigantic registers on the ceiling, up on the ceiling, so that there's a very gentle air coming through, and then the mushrooms let the air return through, like I say, over 100 of those openings. So not only is it well distributed across a lot of openings, but it's also very even because those are distributed throughout the sanctuary and very nicely underneath each pew, so that the air gets drawn nicely down and sucked into the return air of the furnace. How it gets there is the interesting part. If you've looked at the sanctuary, I don't know if I'm going to be able to draw this or not, but if you look at the sanctuary cross section, if this is the back here, and then up here is like the chancel and all that, it's actually ranked. So it slopes. Like this. And then all these mushrooms are here. And there is a miniature floor. There's a crawl space in here that's about 2 feet to 1 feet in height. And it's the entire sanctuary that is sandwiched between the floor of the sanctuary and the ceiling of Ackerman Hall. And that becomes the return air plenum. And then there's also some vents out here in the narthex that bring in air that way just through the wall. And then underneath the chancel is where it all happens. There is all sorts of things underneath there, but for this purpose there is some ductwork that hooks in and then takes that entire width of the building and narrows it down into ducting through some very interesting metal fabrication, and then channels them like this down into the return air for both S1A and S1B, and as we'll find out also for the narthex. So that's the return air path for the sanctuary. Okay, so the narthex is an S4 furnace. Same kind of deal here. Fancy artwork. Its return air is coming from the same place. It shares the same return air plenum because its vents, its inlet for the return air goes right into that false floor, and that's where the air gets sucked back into both S1A, S1B, and S4. So they kind of have to be used in tandem, and as you'll see on that card in terms of best practices, you really want to use these in tandem, and we can go more into that later, but it's fairly ingeniously designed because the supply air for the narthex goes a couple of places. One, it goes to the narthex. There's 2 large vents on the upper part of the wall over here on either side of the narthex, right by the doors, very large vents. But it also supplies 3 vents on each side of the sanctuary, 1 for each of the big stained glass windows. So it's actually pumping air into the sanctuary space in addition to the narthex. So that's important to remember, since you really can't control one exclusively from the other. But the reason it was designed that way is this is more of a perimeter. So if you think about the narthex, and then the perimeter of the windows is being controlled by this furnace. And this furnace controls the core of the sanctuary. So it makes for a really nice arrangement, because by having the perimeter just a tiny bit warmer than the core, or always running at least, then it keeps the drafts off, and the core, for the most part, doesn't have to be heated much once there's a large crowd in there. It's mostly about air exchange at that point. So by balancing these two, you can get some really nice, even, and energy efficient heating going on. Let's now talk about the 2 furnaces that service the downstairs, and that would be the Ackerman Hall furnace and the classrooms furnace. The Ackerman Hall furnace is S2. S2, Ackerman Hall, and same little furnace deal here. And then we have S4, which is the classrooms. It would also include the kitchen and the bookstore. So Ackerman Hall and the classrooms are in the same floor, the same basic space. So we have this similar situation as we did upstairs in the sanctuary, where we had kind of the commingling but yet separate zones in terms of a common return and a little bit of crossover in terms of heating, but enough distinction to where they could be heated separately. Same thing's going on here. The return air on these is kind of interesting. The Ackerman Hall return air comes through the floor, and there are 2 tunnels that go from underneath the boiler room, the full length of Ackerman Hall, and if you look over by the stairs, the ones that lead up to the bookstore, there are two large floor vents on either side of those steps that go down into the tunnels. Those are the return air tunnels that feed the return air back to the Ackerman Hall furnace. So it looks kind of like this, and then there is a big old box back there, like this, and it has a hole that goes down into the tunnels, so the two tunnels combine, and then it also goes into the classrooms, like this. Wonderful drawings, huh? And there are fire dampers here. We'll get to that in a second. But this big doghouse on here essentially just caps off those tunnels and ports in the return air to these two furnaces, so they can pull their air from there. Ackerman Hall then has supply air, which goes and splits into two places, and there's two large vents up on the upper part of the wall, one on either side of the stage, and that is where the warm air comes in to Ackerman Hall. The classrooms is similar. It splits into two ducts as well, but one goes to the north and one goes to the south and runs the full length of the classrooms. So the one on the south side hits the 3 Sunday school rooms and the nursery, and then jumps over. You'll see an actual round duct in the hallway that goes over into the bookstore, and then the one on the north side goes all the way across through the music room, the classroom, kitchen, and then there's another round tube that jumps across the hallway that goes over to that storage closet for ventilation and heat there. So again, like upstairs, we have a shared return air path and supply air that goes into separate areas. So for example, the kitchen doesn't have a barrier across the serving windows, so the air can go back and forth. So there's some commingling going on there. But for the most part, you have the same concept where the classrooms is intended to be a perimeter, and the Ackerman Hall is intended to be a core. So if you keep the classroom one running and a little bit warmer and constantly running, it tends to keep the drafts off and makes the core only needed for fresh air exchange once it's brought up to temperature and people are in the space. Otherwise it tends to overheat. So it works pretty well by keeping these two kind of balanced in conjunction with each other. Okay, a couple of just details and then we'll wind up this video. On each one of these return air ducts, on all 5 of them, there is a smoke detector. And the purpose is that if it senses smoke in the air coming back, there must be a fire, and then it shuts fire doors. And that's what this is here. This is actually a fire door here, and then on the other drawing where the return air was coming from the sanctuary with all those mushrooms, there is the full width of the sanctuary, but there's also a gigantic door that goes across. There's actually 2 of them that get shut if there should be a fire. These are normally open and they're powered, and if the power goes off, they go shut. But they're powered open unless the power goes off or unless a smoke detector flips. Work, I believe, is that if a smoke detector goes off, if any one smoke detector goes off in a particular area that has a common return, then those units need to be shut down. So if there was a fire in a classroom where this furnace sensed smoke and this one didn't, it's going to shut this one off, but it should also shut off Ackerman Hall. Otherwise, you're just going to circulate not only smoke, but you're going to actually supply fresh air to the fire and greatly accelerate combustion. Same thing upstairs where you have the narthex and S1 and SB sanctuary furnaces. The 3 of them are all sharing a common plane. So the 3 smoke detectors are all wired such that any one of them can trip that. But they are independent of each other in terms of the upstairs versus the downstairs. They do have the capability of being hooked into our security system. At this point we haven't done that, but they do have that feature. Okay, lastly, there are 2 dog houses up on the roof, which we've kind of alluded to. And they are literally little dog houses that look like this. And they have vents on the side of them, and they extend all the way down into the boiler room. So they go 3 stories down. This one is the fresh air, the outside air. And at the very top is a damper. And there's all sorts of insulation they've added to that and so on. So whenever we are in occupied mode and we need to have fresh air, if any one of the furnaces goes into occupied mode, then it activates that damper to open so that it can draw air down. If we are not in occupied mode or all the furnaces are off, then this has a spring return, so it goes shut all on its own when the power gets removed from it. And that way you're not having ice cold Minnesota air in this shaft throughout the day and night when it's not needed. Then there is another one, because if the air comes in, the air's got to go out, and we have to assume the building is not that leaky. So this is called a relief shaft, and it goes all the way down as well. And it's actually a little bit bigger, and it ties into the tunnels that are underneath Ackerman Hall, and it ties into the little mini floor plenum for the mushrooms in the sanctuary underneath the chancel, so that any relief air or any excess pressure then gets blown out. So essentially you have the narthex tunnels here, which continue on over to the furnace, and then you have the mushroom plenum, which continues into the return air of the S1, SB, and narthex, but they're attached or open to this shaft. So if there's excess pressure, then up it goes, and it just goes outside and is vented outside of the building. Now the interesting thing here is there's also a damper on this one, although it's been several years of the project going, and it hasn't been motorized because apparently we didn't know it existed. It's not up here where one would think it would be. It's actually way down here, and it's just a big door. It's not really even a damper. It's just a giant door that right now is shut. These controls were original to the building. This damper here and this one here are original to the building. They used to be controlled by pneumatics, which is pressurized air, and you can still see the lines going down there. For the most part, those have been demoed out of the building, but in this case, the lines are still there, so it just needs to be motorized so it can work with our system. There's all the supply air ducts, the ones going to the classrooms, Ackerman Hall, the narthex, and so on. Each one of those has a fire door in it, which is just a set of dampers. So if you look at the ducting, it's just a set of dampers that are normally open, and they have this little link in there made of like a meltable fusible metal, so that if it gets hot enough, that link melts and these snap shut with a spring. They have to be manually reset, but that keeps the supply air shut off. In the meantime, the smoke detectors shut off the dynamic dampers for the return air.